Okay, yeah. So welcome everyone for this week's ISyE seminar. We have with us Professor Rahul Mazumder, who is the Robert G. James Career Development Associate Professor in the Operations Research and Statistics Group at MIT Sloan School of Management. He's affiliated with the MIT Operations Research Center, MIT Center for Statistics, and MIT IBM Watson AI Lab. His research interests are at the intersection of statistics and mathematical programming, convex and mixed integer optimization, and their applications to industry, the government, and the sciences. Professor Mazumdar is a recipient of the Informs Optimization Society Young Researchers Prize in 2020 and the Office of Naval Research Young Investigator Award in 2018. He's currently serving as an associate editor of the Annals of Statistics and an editorial board member of the Journal of Machine Learning Research. And he will be joining the editorial board of Bernoulli in 2022. So again, very, very excited to have Professor Mazumdar speak today. Thanks again for accepting our invitation. And today he's going to tell us about sparse learning at scale, convex MIP, and statistical perspectives. So Professor Mazumdar, whenever you're ready.
Okay, thank you, Chris, for the kind introduction. Thank you for the invitation, and it's my pleasure to be here. And I really wanted to point out that I have thoroughly enjoyed my meetings since the morning. And I look forward to your questions and comments during the talk. And just to let you know, I mean, feel free to interrupt me at any point during the talk. I have a lot of slides, but it is perfectly fine with me if I do not get through all of them. Okay, so the work I'll be presenting is joint work with Hussein, who is a recently graduate student from the Operations Research Center, who was working with me. He's now at Google Research as a research scientist. Kehan, he's a third-year graduate student working with me. Antoine, he was a student of mine. He is now in Silicon Valley. And Ali Saab was a student at MIT. And Peter Rajdenko, he's a collaborator from the University of Sydney. So I'll be talking about different perspectives on problems that are familiar to many of us, and I know there are people in the audience who have worked on who have done very important contributions to this topic. So the statistical and machine learning estimators that I'll be talking about, these are mostly known. But what is new over here is the perspective with which we are analyzing them. That is, we are basically looking at the computational aspects of these problems, and also in the process, many of the statistical properties of these estimators are coming to light, and a lot of this has been made possible because of computational advances in this area. And interestingly enough, that helps us refine these methods and develop improved estimators. And there is really an interplay over here that I'll get to hopefully throughout during my talk. So what is the overarching goal of this research agenda, if I may put it that way? This is something that is known. That is, many high dimensional or statistical problems, they are inherently discrete. Okay, so what do I mean by that? That is, if you think about problems like variable selection, or problems like classification, building decision trees, robust statistics, and so on and so forth, there is an element of discrete choice involved over here, right? So is a variable going to be in or out, and so on and so forth. So they can be naturally thought of as discrete problems. Now, continuous and especially convex optimization has played a significant role in developing principled algorithms for these estimators and these methods. And also they have provided a framework to understand the statistical properties of these methods. Okay, and this has happened over the past several years, and it still continues to play a very significant role. Now, what we are asking at this point is, can we go beyond simple or standard convex relaxations, or simply by applying a heuristic method to a problem, we would get a good feasible solution, right? So the question that we are asking over here is, can we do better than just a simple, a good feasible solution? Can we get better solutions? And the other part is, okay, can we do something better than just using a convex relaxation for the problem? Can we refine the solution in some way? And to that end, can we use techniques in discrete mathematical optimization or mathematical programming, broadly speaking? So one of these things that I'll be focusing on in this talk is, can we consider these integer programming problems or discrete problems? And then can we use these ideas and also ideas from convex optimization to scale up discrete problems? There is also another place where which goes the other way. That is, we can think about a convex problem and think about scaling it up. Okay, and many of the methods that are used, for example, methods like active set or methods which are commonly used in OR, like column generation and constraint generation, some of these are inherently discrete optimization techniques, but they can actually help in scaling up convex problems as well. So that's the other direction that I'll not talk about in today. I'll mainly talk about, are these ideas from discrete optimization, can they be helpful in scaling up statistics problems? And in the process, we would also see that convex optimization has a significant role to play. Okay. All right. So one of them is a computational part, right? But then, of course, some questions arise. That is, we would like to solve machine learning problems for our statistics problems at large scale, or we would like to stretch, we'd like to examine or understand how big problems we can actually solve. Okay, so, and with what times? So that there is a notion of computation practicality that arises over here, right? So if you give me a 2 hours time window, can I solve this problem or not? With what accuracy? Versus if you give me a 1 minute time budget, then what can I hope to get? Okay, so there is a notion of computational practicality also depends upon the context. So this is something to keep in mind. And here is the other part, right? So statisticians and machine learning people have thought very hard over the past several years to come up with excellent estimators with very good statistical properties. So the question over here that I want to ask is that if we are using these discrete mathematical optimization methods to solve these statistical problems, what is going to be the statistical properties of these estimators, right? So how are they going to compare versus estimators that are usually available to us based on current state of the art? Okay, so these are two questions that I would like to answer or understand. All right, and this is the way in which we are thinking. I think about the problem. That is, in order to address these problems, addressing these problems actually leads to an interdisciplinary approach. We need techniques from different fields. Okay, so for example, of course, high dimensional statistical ideas are going to be needed. Convex optimization ideas are going to be needed. And I put a very strong edge over here because it is known that there is a very strong link between convex optimization and high dimensional statistics. On the other hand, there are some links, I would say, between integer programming and convex optimization. There are historical links between convex optimization and IP. But when it comes to scaling up these problems, integer programming problems, to very large scale instances, I think, again, this is my viewpoint, I think we really need to understand how large-scale convex optimization methods can help us scale up MIP problems, okay? And that's some of the exploration that we have been doing, and I'll be sharing with you some of this. And then, of course, there is a link between, can MIP integer programming help in solving these statistics problems? And the other thing is, okay, once we understand the properties of statistical methods, can it help us, can it lead to new questions that integer programmers can investigate? So this was abstract. So let me now give you some example problems. Okay, now these example problems that I'll share with you are biased examples because these are examples that I've worked with over in the recent past. But just to illustrate, I'll give you some problems which can be naturally cast as integer programming problems. I'm not claiming that just if you formulate a problem with integer programming, the problem is solved. No, I mean, it's just the beginning. A lot more interesting research needs to be done afterwards. Okay, so one problem is the problem of grouped variable selection. Okay, so this is a very well understood problem. This is a very commonly known problem in the statistics and machine learning parlance. Basically, what happens is you are dealing with variables with these variables, because of spatial proximity or because of temporal proximity, and so on, and physical proximity, these variables often occur in groups. Okay, so so if you basically are going to use a binary variable to decide whether a group is going to be active or not. And this is a work that I recently did with my student Hussein and Peter. So we study a collection of these problems, which involve groups structured sparsity, and we study some of the statistical as well as computational aspects for this. Okay, there is also actually a very important problem class that arises in non-parametric statistics. That is, these are known as additive models, where the conditional expectation of y given x can be written as as a sum of individual fits. Okay, these individual fits fj xj, xj is the jth feature, and this is going to depend upon a small sum of these entries. fjxj, this is a function, and this is going to be a smooth function. We do not know a priori what the function is. All that we know that it is smooth. Okay, so these are this is a very well understood family of problems in statistics, and is used in the context of non-parametric additive models. And it turns out that if you want to do variable selection in the nonlinear setting, unlike the linear setting, then these problems can also be reformulated as a optimization problem involving group structures. So this is one example. Now talking about.
Sorry, Rahul.
Yeah, sure.
You mentioned what were you assuming on the set S? Did you say that that's a small subset of the set of variables?
Right. So I wasn't very clear, but S can be a very small subset of features. So let's think about, you have a data frame where you have, say, 500 features. And out of that, you want to do a model like this. And then S is going to be a set of size, say 10 or 15.
Right. But it's unknown to us initially.
The set is unknown. Yeah. S is unknown.
Yeah.
It's like variable selection. Yes, exactly. It is unknown. Okay, so here is another example of structured sparsity. And this is, again, this problem also has a very long tradition in statistics. This is known as what is known as a hierarchical sparsity problem. Okay, so we are in the linear model space, right? Expectation of y given x is given by a collection of models of linear effects as well as interaction effects. And over here, xi times xj, these are the interaction effects. And then we want to fit a model subject to the fact that the number of non-zeros in beta and theta, these guys, they have to be small. And also there is an additional interpretability constraint, which is often known in the literature as a hierarchy constraint. It says that if the effect between I and j, if the effect is non-zero, then the parent effects also have to be non-zero. Okay, so this is an interpretability constraint that is often used, and it has a very long history in statistics, and people like to use this while building models. Again, what I just did is I just took an estimator, which has a very long existence in statistics, and then immediately you see that there is a very nice combinatorial structure in this problem. Okay, so in this work, there is so there was a talk that my students presented at Informs recently on this topic. But in this place, this is a place where IP ideas can be very useful. Okay, and it can be useful in a very curious setting. There are a bunch of penalties, convex penalties, that have been proposed for this. Okay, now what we do over here is we just write down the problem, the IP problem associated with it, integer programming formulation for this. As soon as you write this, you can relax it, right? And as soon as you relax it, that leads to a very simple looking, nice penalized framework, a convex framework, which imposes a structure like this. Okay, so this is a place where I think, at least in our experience, we found out that IP principles, or modeling principles, or OR modeling principles, broadly speaking, that helps us formulate a problem, and it immediately leads to a simple and intuitive penalty, convex penalty, for these classes of problems. Of course, scaling these problems is very hard, and even scaling a problem of this size for the convex problem becomes quite challenging. And this was the focus of a work that I did with my student recently. Okay, here is another problem to the problem of structured sparsity. Another example where we are using a classic method in statistics, modeling tool in statistics. And this is a paper that we wrote with some collaborators with Emmanuel Ben David, who is at the US Census Bureau. So what we are trying to do over here is predict census survey response rates, right? And we are trying to predict that by using a collection of independent variables. All right. Now, if you use a linear model, which is one of the methods that is there is some discussion around these methods on the Census Bureau website. That is known as a low response score. It is based on a linear model. It turns out that the linear model predictive power is not that high. Okay. And if you really want a model to predict census response rates very well, you need to use non-parametric models. In fact, a few years back, there was a competition on this. And it turns out that the best predictive models were based on random forest and on ensemble of methods. But there was a follow-up article on this. This was quite some time back, 2013 or 2014, if I remember correctly, where they said that these predictive models, which are very good, by the way, in predicting census survey response rates, they could not be used because they were not interpretable, as they were using black box methods. And also they started using features which were not really actionable. Okay, you cannot take any action on top of that. So what we did in this work is we revisited some of these methods, which are known as additive models with interactions. Again, FIs and FIJs, these are unknown functions. And to the question that Nick was asking before, I and omega, I do not know what these subsets are. All that I know that these are small subsets. If I build a model like this, again, this is a well-known model class, right? But there are no existing algorithms for this. And the number of data points over here is easily of the order of hundreds of thousands. So scaling up these problems become pretty challenging. So we do see that if we develop new computational techniques, then it turns out to work quite well. In fact, in terms of prediction accuracy, it turns out to be comparable to methods like XGBoost and random forests, but it gives you a lot more. For example, you can see there is an interpretability associated with it, which is possible with these methods. Okay, so another problem, again, where it's the case where structured sparsity arises. And I know there are people in the audience at JP, and they have worked on this problem before recently using very nice integer programming approaches. Here is one take on the problem, right? So the sparse PCA problem using integer programming methods. Okay, so the L0 sparse PCA problem is basically given by the following problem. You're maximizing a convex quadratic subject to a cardinality constraint and an L2 norm constraint. It turns out that this can be written as an MILP, but it's difficult to scale. So what we do is we relax this problem. We relax this one into an L1 ball. This is still non-convex, but it turns out that this one is more amenable to integer programming techniques with current technology that we have. And this is joint work with Shantanu from Georgia Tech and his student Guani. Okay, so this example was a problem where, again, so we take a problem from statistics and then we try and explore what integer programming methods can be used for this. But here is a different take on the same problem. Okay, and the take is the following. I'll say that this is the original version of the sparse PCA problem. Okay, now what I'll do is I will take into account an underlying statistical model under which the theoretical properties, statistical properties of this estimator has been established. Okay, so what I'll do is I'll take into consideration the fact that there is an underlying statistical model which is generating the data, which is known as a spiked covariance model, by the way. I'll also assume that the data is generated from a Gaussian distribution. Okay, so if I take that as a starting point, then what I can do is I can use the properties of the statistical model to reformulate this problem. Okay, it's not going to be a mathematically equivalent reformulation, but it is going to be a reasonably well justified reformulation under statistical assumptions. It turns out that if I do this, it turns out to be a integer programming. It's going to be a mixed integer quadratic programming problem, but it resembles very much a subset selection problem that I'll get to very soon. And that problem turns out to be scalable to much larger instances. For example, using this approach, we can scale up to problems with 20,000 features. Okay, again, it is not exactly solving this problem, but in a certain statistical sense, it is getting at a good solution to this problem. Okay, so this is a place where statistical ideas can help us reformulate an integer programming formulation into something else, which turns out to be easier to solve, quote unquote, using current techniques in integer programming. Okay, so I think, again, the integer programming formulation that we have, again, this is probably going to be NP hard from a worst case viewpoint, but the current technology is we have seen that the current technology is very good at solving some classes of IPs, whereas it can be not so good in solving some other classes of IPs. Okay, so basically what we have seen is that, okay, there are these problems in structured learning, and then we have integer programming methods. And as you know, these are one of the good things about these integer programming methods is it gives you a certificate of optimality by using in the form of a branch and bound tree. And this is, I would say, a very nice thing that we get from the integer programming framework, because in many of these non-convex estimators that we see in statistics, like the best effort selection and so on and so forth, many of these estimators, when we derive statistical properties of this, I'm not saying that all of them, in many of these cases, we assume that we have a global optimum solution to the problem. Okay, now it would be good to know, that is, if we are at a global minimum or if we are near a global optimum minimum. So the branch and bound tree gives us a certificate towards that. And this is really not available if you are using heuristic methods, because it doesn't really give us a certificate of optimality. And if you also have a certificate for optimality, that can also be translated to suboptimality guarantees in terms of statistical properties. Okay, so what are the good things that IP has given us? Okay, so for example, it allows us to do simple prototyping. So for example, with Julia, Python, and Mosaic and Gurobi, you can basically, with very little time, you can set up a problem, especially for people in OR who are very familiar with these tools. They can set up a problem very easily and then see how it applies on their problems. And many commercial solvers are very powerful commercial solvers exist, such as Gurobi and Mosaic, and they are getting sped up every year. And most importantly, I would say that if you can actually formulate a problem using these techniques, you can run preliminary experiments to understand the properties of this, the statistical properties of this estimator. And if you really see that this estimator works well, then probably it's a signal where you need, and if you, where more specialized algorithms have to be built. And in some cases, it can give you a guidance that this estimator is not working well in some regimes. And in that case, you probably have to go back and think about the statistics of the problem and think about modifying it. Okay, so along with pros, there are going to be some challenges. And basically, I would say in some cases, problem-specific algorithms and tuning is often required. And some of these commercial solvers, if they take 5 hours versus 20 days, we really do not know at times. It's not very clear. It doesn't tell us why it is being slow, okay? Because they only give you a snapshot of what is really happening. Okay, so hopefully by this time I've convinced you that there are these 3 things that are happening, 3 boxes that are out there, right? The structured learning over here, convex optimization, and MAPE. And there is a lot of action that has gone on between these 2 areas. But on the other hand, there are, I mean, I think these dashes need to be better understood, okay? And more research is needed to be better understood, to better understand these links. And the remainder of the talk, so thus far, I have given you very high-level examples as to where integer programming formulations can be used to model structured learning problems. In the next part of the talk, I'll basically share with you my experience where we want to scale up integer programming problems. And in order to scale up integer programming problems, we would be using heavily ideas from convex optimization. Okay, and I'll give you another example where we really want to solve a very large scale problem in structured learning. And it turns out that in order to do that, we would be using ideas from both convex optimization as well as integer programming. Okay, so it's basically I do not have a very I do not have a solution which basically uses one of these boxes, but it's basically spanning all these areas. Because eventually the goal in a certain sense is to see how these algorithms can be used in conjunction with each other so that they can lead to better solutions from a statistical viewpoint, and also to try and understand when we get better solutions. All right, so now I'll make things less general, and then I'll talk about a very specific example in the context of L0 sparse regression. All right, so what is a stylized setup? Okay, so again, this is a very stylized setup. And we need a stylized setup because when we talk about properties of a statistical estimator, it always helps to have a very well principled setup and to discuss about the properties of your estimator. All right, so let's assume that the data is generated from an underlying linear model. By the way, when we use sparse regression and things like that, you do not necessarily need to assume that there is an underlying truth, but let's assume that there is a sparse ground truth, that is y is generated from an underlying linear model, beta naught is sparse. Okay, and these are the dimensions. I'll basically assume that there are n samples and p features, and the errors and noise is distributed. The task over here is, given data, I would be estimating beta naught by beta hat. Okay, now there are many ways to do this. In this talk, I'll be focusing on an optimization based method to do this. And you'll see very soon, I'll be focusing mainly on discrete optimization methods to do this. Now, usually in the statistics parlance, when you have an estimator beta hat, right, how do you judge whether an estimator is good, right? You look at properties like this. If the underlying beta naught has, say, 5 non-zeros, does beta hat give you exactly those 5 non-zeros in exactly those 5 locations? That's a question of full support recovery. Now, this may not be possible in many cases. It may be possible in some cases. There are information theoretic limits to this. We may also want to understand how close is beta hat to beta naught, for example, in an L2 distance. We may want to look at prediction error. So prediction error is going to be how close is X beta hat to X beta naught. Now, in some cases, what happens is you may not be able to get a model which does full support recovery, okay? Or you may not even know what the underlying truth is. In those cases, you may still be able to look at prediction error, okay? Because you have a held out test set, you look at prediction error, but then what does compactness, what will you do with L0 minimization or sparsity? This is basically going to give you a trade-off with prediction error versus the number of non-zeros that you have in your model. Okay, so loosely speaking, I would say the number of non-zeros in beta hat, it relates to interpretability constraints. So of course, interpretability can be much more complicated than just counting the number of non-zeros. The other thing is it can give you model compactness, right? So in many application areas, actually, the model compactness can be an important consideration, and especially when you have a model with many parameters, having a model with few non-zero parameters can be beneficial. Okay, so in order to target problems like this, right, the statistical landscape is going to tell you that there are many ways to do this. Okay, and these are some candidate canonical estimators, because this problem has been very well studied in statistics. Okay, this problem class, and there are many estimators to do this, right? So one of them is written by an optimization formulation, which is the L1 or the Lasso. This one is the L0 or the best subsets problem. Here is an algorithmic way of thinking about the problem, right? This is, by the way, this one is not a minimum. This doesn't solve any optimization problem, by the way, stepwise or boosting. So it is an algorithm. You apply an algorithm on this loss function, and then if you run it for 5,000 iterations, you will get a certain solution. If you run it for 2,000 iterations, you'll get another solution. Okay, but it can give you good solutions. These are given by optimization problems. Of course, this is given by a structured integer programming problem. This is given by a convex problem. I would argue that there is a lot of work that has been done on this problem, but a lot remains to be explored in understanding the computational and statistical properties of this guy, as well as on this problem. Okay. All right. Again, what is the best method? There is no best method. I mean, of course, there is no free lunch, right? It depends upon the data. It depends upon what your N is, what is P is, what is X is, what is beta naught is, what is epsilon is. And in some cases, actually explaining what is going to be good or bad, it becomes very nuanced. It depends a lot upon the scaling of N, P, the conditions on X and Y, and so on and so forth. It depends upon the problem. But the point is, can we have actually tools, principal computational tools, with which a practitioner can use these different methods on their application task and then figure out which one actually works well for them. So, and also it is important to understand these methods from a methodological viewpoint, right? Because in some cases, once we have a methodological understanding about some of these problems, it can provide useful guidelines about what can be used in practice. All right, so now I'll be focusing on this guy. On the subset selection problem. Now let's talk a little bit about the computational paradigm of this. Okay, so Pre-2016, so this particular problem, okay, this is a hard problem, of course, right? And not some time back, like a few years back, if you threw it into an R package, this could not solve very large problems. Okay, now the question is what happens in practice. So in a paper with Bertsimas and King, we formulated this problem using integer programming, using an integer programming framework. And then basically with a little bit additional work, using some other, like using advanced warm starts. Again, advanced warm starts came from developments in continuous optimization. Using advanced warm starts and then a few choices in around big M, if you formulated this problem and put it into a commercial solver such as Gurobi, you can get reasonably good solutions. All right. And in a sense, okay, so this kind of helps us understand what the statistical properties are. Okay, because you now have a framework with which you can compute solutions to this for problem instances that were not possible before. This helped demystify some of the statistical properties of this. Okay, because a lot of the statistical properties of this estimator was not known. And thanks to the IP-based methods and optimization methods, we could compute them. And then we can examine or systematically do experiments about what are the statistical properties of this. Of course, not always does it work well. In some cases, it works very well. In some cases, it doesn't work as well. Okay, so, and some of these things were brought to light in a very nice discussion paper by Hasty, Tipshirani, and Tipshirani. And then they raised out some issues with the statistical properties of this. One of them is that if you have a lot of noise in the problem, right? If there are a lot of noise in the problem, which is also known as low signal to noise ratio, then the statistical properties of this, that is the out of sample properties of this, it doesn't work. It is not very good. Okay, so it can be actually very bad, and it can be and there are many other estimators which have statistical properties much better than this out of sample prediction. So there are cases. Yeah.
Rahul, again, just a clarifying question. When you say statistical properties, I think you were just clarifying this point on kind of what you mean, but so I should be thinking of out of sample prediction.
Yeah, just think about out of sample prediction.
Okay, great. Thank you.
I'm being a little vague over here.
Is the problem one of overfitting?
Yes. Yeah. So basically what happens is there is a lot of variance. This guy, I mean, there are many ways to intuit about this. Basically, if you think about this estimator, right, it is searching very hard for a collection of k non-zeros. So in the process of searching, it spends a lot of degrees of freedom, if you may put it that way, to find out a subset of 5 features. This is one. And the other thing is, once it selects, there is no shrinkage that is happening. Okay, so these are the reasons why. Again, the two statements that I told you, right? I cannot math. I mean, this is in some sense they can be mathematically quantified, but it is not very. But there is another way with which you can basically show that the statistical property, the error bound of this is going to be larger than it's going to be bad. You can actually show that in theory, but I'm trying to give you some intuition as to why this can happen. Okay, and the other part is computation. It can be slow for practical usage. Okay, that is, I mean, they basically showed an example where they said that, okay, if I have a problem with NP equals to 1,000, and because statisticians in general do not know what the value of k is going to be, right? You have to do cross-validation type of things to find out what the optimal value, what is the right value of k on the data set that you're given. Then you have to run these problems for many folds for many values of k. And if you're solving an integer programming problem for so many values, it is going to explode. The runtime is going to explode. Okay, so these are valid points. So now what I'll go over is I'll talk about some ways by which these can be addressed. Okay, again, thanks to integer programming methods, these were some of the less understood aspects of the statistical properties of subset selection. Thanks to integer programming methods, we are now being able to understand what the statistical properties are. And once we can understand what the limitations are, we can think about improving them. Okay, so let's first talk about the statistical limitation and ways to think about how to mitigate this. Okay, so what we propose is actually a very simple fix. So, okay, to the point that was raised just before. So what actually happens when the signal to noise ratio is low? Basically, best subsets has a very high variance. And in some cases, actually, if the noise amount is very high, then it is actually not difficult to come up with counterexamples. You can come up with counterexamples in a very, very stylized settings easily. That if the amount of noise is very high, it may be virtually impossible to identify what the true features are. It's just information theoretically intractable. You cannot do it. So in these cases, finding out the right set of features is not possible because of noise. Okay, then what can we do? Because in reality, we would be probably facing a situation like this. I'm not saying all situations are like this, but in some situations where you expect the amount of noise to be large, you still want to fit a linear regression model with some penalization. You do. You would like to have models that have good prediction error. Good prediction error means out of sample, and also have nice compactness properties. That is, it doesn't have too many non-zeros. Okay, so these are two conditions that I need. If I want these two conditions, then here is a proposed estimator. Okay, and this estimator was proposed in a paper that I wrote with Peter Radchenko and Antoine Didou. And what it does is it basically combines the best of both worlds, right? So if you think about Q to be equals to 1, this is the lasso. Okay, and let's forget about this penalty. And this is a lasso estimator. In fact, what happens is when the amount of noise is very, very high, when the signal to noise ratio is low, the lasso actually does very well in terms of out of sample accuracy prediction. But if the amount of noise is very low, then software selection turns out to work very well. Again, I'm simplifying, but under some cases, you can actually see that this happens. All right, so our point, so the point of this estimator is, okay, why not combine the best of both worlds? Okay, and it depends upon the person whom you talk to, right? So for people who are Bayesians, for them, an estimator like this is going to come very naturally. So, okay, so this is the proposed estimator. It does shrinkage as well as selection at the same time. Okay, so the thing is, this again is written as an integer programming problem, can be written as an integer programming problem. And okay, so there are going to be computational issues that I'll get to very soon. But before that, I proposed an estimator. So, and in this paper, we also show that, so this is the same paper. It was revised in 21. So in the same paper, we actually show that this estimator has actually provably better prediction accuracy compared to pure L0. That is a L0 where you do not have this guy. This is a vanilla best subset selection for low signal to noise ratio problems. Okay, so you can actually demonstrate that this has superior statistical prediction error performance compared to the basic version of the best subset selection problem. Okay, so there are other approaches as well that have been proposed. So for example, relaxed lasso is another approach that has been proposed because the lasso, it turns out that lasso does not work very well when the signal is very high. So the relaxed lasso has been proposed to kind of get the best of both worlds, of both high signal regimes as well as low signal regimes. Okay. All right, so now I'll talk about the computational aspects of this. All right, so okay, so I have like 20 minutes more time. Okay, so there are two parts to the computational story. All right, so one part is getting approximate solutions. Okay, and these approximate solutions, of course, I mean, they are for practical usage, because if someone wants a solution which very fast, they probably do not want an optimum solution. Okay, but of course, the next part is if you're curious about learning what the how close the solution is to an optimum solution, that's the place where we need another method, which basically does branch and bound using first order optimization at the node relaxations. These are the methods that give you optimality certificates. Okay, so what I'll do is, these are two methods. I'll first talk about approximate solutions, and then I'll talk about optimality certificates. I know I do not have much time, but I'll give you an overview of what is happening. And if you're curious, then please feel free to have a look at the papers. But again, there is a synergy, right? Because when you're doing a branch and bound, it always needs a primal feasible solution, right? Good feasible solutions it needs. And that's the place where these methods are going to be very useful. Okay, so let's first talk about this guy, right? Best subset selection using coordinate descent and local combinatorial optimization methods. Okay, so coordinate descent is a classic method in continuous optimization. Okay, so we look at a problem, we apply coordinate descent. It turns out that coordinate descent does not work very well in some regimes, in some problems. and the quality of the solution turns out to be is not that good. So we want to improve it. And in order to improve it, we start using local optimization ideas, like local combinatorial optimization ideas. And with that, things start improving. All right. So what are the key ideas of our approach? So the ideas of the approach is we want estimators based on approximately solving this. So let's assume Q is 1 or 2, and I'm putting everything together under this setup. Q is a fixed number, and this is our estimator. What we do is, what probably a continuous optimization person is going to do, they'll study the different necessary optimality conditions for this problem. And then based on that, studying that, they will probably think about coming up with algorithms for this. Okay, so that's what we do. So we look at a bunch of necessary optimality conditions for this, and that gives rise to algorithms. And basically, there are two types of methods that we use. One of them is based on cyclic coordinate descent. Again, why are we using cyclic coordinate descent? Okay, there are many reasons, but one of the main reasons is, if you think about the algorithms that are used to solve very large-scale lasso problems like GLMNet or even non-convex penalized regression, they actually use coordinate descent as one of their main workhorses. And there is a lot of problem structure that coordinate descent can exploit very well. That's what we want to use for this class of problems as well. Now, local combinatorial search is inherently, it's the way in which we write it. It is going to solve small scale integer programming problems. And it turns out that this can actually help significantly in terms of statistical properties. Again, these statistical properties, this statement that I'm making in this case, this is an empirical observation. This can actually help significantly in terms of statistical properties, especially variable selection properties in some cases. Okay, so these two things together, they are actually really helping. Okay, so this is a place, again, to go back to the landscape that I was talking about, right? Continuous optimization is definitely giving us very fast algorithms for this. But then when it gets stuck, if you are thinking about a principled way to improve the quality of the solution, that's a place where integer programming is going to give you ways. I'm not saying this is the only way, but integer programming can give you ways to improve the quality of the solution. Okay, here is an informal description of the algorithm. So basically, we run cyclic coordinate descent to optimal local minimum. So this is, let's say, this is the local minimum that you obtain. S and S complement. This is the support, and these are the zeros. You take a few, you take some entries from over here, non-zeros, and you try to make them 0. And you take a few zeros from here and try to make them zeros. Okay, and you control the number of guys that you're changing. So this is the swap operation that can be read as an integer programming problem. Of course, if the size of the swaps, if the swap size is small, then it can be done from scratch. You do not need integer programming solvers. But it turns out, and we have several experiments on this in the paper, if you actually do this in some regimes, this can actually help improve the statistical performance of the problem. All right, so this leads to, as you can think about a hierarchy of optimality conditions, right? So for example, these are the pretty low quality solutions, stationary solutions. You can think about iterative Hart thresholding type solutions, like which are basically proximal gradient type methods for this problem. If you study the stationary conditions for this, they define a certain class. It turns out that if you look at the stationary points corresponding to coordinate descent, it turns out to be a smaller class compared to the iterative Hart thresholding. And the main reason is because of the step size that IHT uses and the step size that coordinate descent uses. These different step sizes, and because of the step size difference, the stationary solution, the family, you see this nesting behavior. All right, and here is a place where you see more improved solutions when you start doing integer programming into the mix. So there is a difference between PSI and FSI. This is partial swap and this is full swap. I'll not be talking about the details of this, but there are some difference between the way in which you're doing the local optimization. Okay, so I told you a lot of methods. Now let's see how it actually works in practice. Okay, so again, so we want we want fast algorithms. They are not going to be they're not going to be optimal. They are going to be approximate. So let's see how it works compared to other methods, right? So GLMNet is a very fast implementation for the lasso. NCVReg is a non-convex method, heuristic. It's also based on coordinate descent. All these methods, interestingly, are based on coordinate descent. And L0learn is our method. Okay, so this is a US Census data set with speeds 55,000. These are approximate solutions, and we are getting the time in seconds to compute a path of 100 solutions. So basically, long story short, what you see is that in terms of time, L0 learn can be comparable to the Lasso. In some cases, it can be faster. And this is because L0 learn gives you much compact solutions. So let's look at the number of non-zeros that you have. So so this is the optimum solution based on validation tuning. You see that in terms of MSE, test set performance, okay, L0 learn is good. This one is also good. GLMNet is also good. The number of non-zeros, that's the place where you see a big difference, okay? And again, in this case, where you have 175,000 non-zeros, you get an approximate solution in say around 30 seconds. And the number of non-zeros, again, there is a big difference over here. So what are we achieving over here, right? If I want to summarize. So I'm proposing over here an algorithm, which in spirit tries to have the characteristics of a solution to this particular problem. Okay, it may not be the optimum solution, but using techniques from coordinate descent as well as integer programming, we are hopefully getting a high quality solution. Okay, so now let's talk about the experiments and the statistical performance. So in terms of statistical performance, okay, so there are many experiments. I'll basically show you one example. Okay, so what this basically looks at is, okay, so this is the probability of full recovery. So 1 means very good, it is recovering the entire support, and 0 means it is pretty bad. All right. So L1 over here, these are the L1 based methods. Probability of full recovery. This is an example that we have chosen such that L1 is not going to be able to recover the support. Okay. There is something called L1 relax. It also doesn't do very well. L0 CD, this does not do local search. This does local search. And the local search over here, swaps that we do, we are basically moving one of them at a time. And this runs basically in milliseconds. Okay, this also runs in milliseconds. And what do we see? We see this is the real power of convolutional search. So in terms of variable selection performance, you're actually seeing a big gain if you're using local search compared to not using local search. Okay, so this is a place where I would say integer programming ideas are really useful. So there are many other examples over here in terms of prediction and so on and so forth. And in some cases, basically the correlation level is low. The difference actually goes away. So what I'll do is I'll just basically skip through this through this part. And then I'll basically say that, okay, some of these methods can be extended to the case of classification. Okay, and then, okay, let me talk about the remaining 10 minutes that I have, some notion about some of the techniques that are used to get optimality certificates. All right, so this project was very, well, I mean, the earlier project was also very interesting, but this one was really interesting because we were basically exploring an area that we did not know very well, because it's basically how can you actually solve these problems to optimality, these integer programming problems, using branch and bound methods. So what is it that we are doing? We are writing our own branch and bound solver. Okay, and if you're writing our own branch and bound solver, at every node, you need to solve a convex relaxation. And that convex relaxation, we are solving by using first order methods in convex optimization. Okay. And again, so is our branch and bound software comparable to very fancy implementations? Probably not. But we are exploiting a lot of structure in the first order optimization methods in solving the node relaxations, which is giving us a significant edge, I think, at least in many of the examples that we have tried. Okay, and this is completely open source. The previous package that I told you about, the method that I told you, that is also open source, that is written in R, and this one is written in Python. So, and it does not use any commercial solvers at all. I mean, it's written completely in Python from scratch. So it's something which is very easy and portable. And if you want to understand when it breaks down or when it works well, it's very easy to play around with. So this is joint work with Hussein and Ali. Okay, so I must say that there has been a significant interest from the integer programming community about coming up with algorithms for this, and many exciting new ideas have been proposed. And there is one class of methods that have been proposed by Bert Simmers and Van Paris and co-authors, where they are using a method based on cutting planes, right? So to address this problem, this actually works very well also. But this uses, as one of the main workhorses, it uses a Gurobi, a very good commercial solver to solve an MILP. So it's an iterative process, and at every iteration it needs to solve an MILP because it's an outer approximation method. And for solving that MILP, it actually uses a commercial solver, or you can use other solvers as well, but Gurobi is very efficient. That's what it uses. Okay, so all right, so let's talk about our approach. It's of a different flavor. So we look at this problem, and then, as I said, I'll propose a standalone branch and bound method, right? So this is basically a snapshot of the branch and bound method that is produced by our algorithm. Okay, so for the first time, I would say this is actually interesting because we can actually see how the branch and bound tree looks like, what is the depth, what is the breadth, and so on and so forth. And this is a real problem, actually. I do not, okay, I can see. So this is a problem where P is the number of features is 100,000, the number of samples is 1,000. So this is a problem that is being solved to optimality with P equals to 100,000. Okay, and this is based on this. And the chances are, if you're throwing this problem into a commercial solver, it is probably going to take hours to just solve the node relaxation. Okay, and this is a place where actually the structure of first order methods, at least we found it to be very, very useful in this exercise. All right, so what is a key driver? And this is the reason why we really were ambitious in exploring this direction. That is, okay, we kind of leveraged the understanding of how to scale up large-scale convex optimization methods using first-order methods. Okay, and that is, I would say, that is one of the key drivers in scaling up this problem. So at every node over here, you would be solving a convex optimization problem, and that convex optimization problem is going to be pretty large. But it turns out that if you solve these problems using first-order methods, you can get a primal feasible solution as well as you can get a primal solution as well as dual bound. You can get them very efficiently if you work. Some work is needed, of course, but it turns out that this is doable. Okay, so this can solve up to, I think the largest example that we tried is beta. The length of beta is up to 1 million features, and the number of samples, actually 1 million or 10 million, I forgot. But anyway, it's pretty large, up to 1 million, definitely. And then these are the classes of problems that we can address with this method. Okay, so now, again, so the node relaxation turns out to be a second order cone program. The relaxation solver is basically based on coordinate descent. And this is, I would say, conceptually is something that makes our method different from what Gurobi or Mosaic uses, as far as we know, because they would be using probably an interior point method or probably an outer approximation method. Anyway, whatever they use, I think our use of first order methods for the node relaxation, that seems to be one of the key differences. Even though our branching method is not as sophisticated or not well implemented, I think this is the thing that is really making the difference. In terms of branching, we tried several branching methods. We found out that an approximate strong binary branching to be quite useful. Again, there is a lot more that can be done over here. We have basically tried some approaches, but there is a lot more that can be done over here to explore what type of branching rules are going to be useful. One of the key things that you really need for the branch and bound tree is you need a dual solution, right? So at every node, you need a primal dual gap. And then in order to do that, what we do is we use coordinate descent, and coordinate descent does not naturally give you a dual solution. So we use coordinate descent, we look at the KKT conditions of the problem, and then we produce a dual feasible solution from that and from the primal solution. Okay, and this is very useful for us because without this, you cannot terminate this in a principled fashion. So let's see what happens at the node relaxation. Okay, so this is the original problem. Okay, and this is a place where we start with IP principles, integer programming principles, right? What we do is we write down the perspective formulation of this. So I used a ridge regularization over here. We use the perspective reformulation of this. Beta i's, we are assuming it has a bound, and it is beta i's are bounded. Okay, so and this is the formulation that we use. And for those of you who are familiar with this, you'll know, I mean, there is a long tradition of this method, of the use of this method in integer programming. This is known as is actually a mixed integer second order conic problem. So basically, as a second order cone problem, SOCP, where some of the variables are going to be binary. Okay, and it has actually very good relaxation properties. And we show some of these, and there is earlier work, of course, which shows properties around this, the fact that the relaxations over here are good. All right. Now, since the key is how to solve the node relaxation, let me walk you through some of the tricks that we used. So ZIs are binary. Okay, so you just relax them, reformulate. Okay, so this reformulation is very important, because if you just write the ZIs to 0 and 1, you'll get a lot of variables. You'll have an extended formulation, right? We do not like the extended formulation. We don't like the extended continuous formulation. We do not like, because the main reason is because if you have a gigantic formulation with lots of beta and Z and S variables, developing a fast and efficient solver becomes more complicated. Okay, so that's why we look at this problem, we try to do some reformulations on this, and this is the problem that you get. Okay, and this is the problem that we attack, this guy, with first order methods. And it's actually very interesting, because this actually gives us some insights from a statistical viewpoint about what is happening. Because this penalty turns out to be what is known as a reverse Huber penalty, right? So the penalty looks something like this. It's yeah, so this is how the penalty looks like. Okay, so it's kind of a convex combination of the ridge penalty as well as the L2 penalty as well as the L1 penalty. But the point is that this particular problem is in the of the composite form. So this is amenable to first order methods in convex optimization. So here are some relaxation tightness results that are there in the paper. All right, so how do I solve this? So this is basically solved by cyclic coordinate descent, and there is a lot of tricks that are used over here. So first of all, active set updates are used enormously, because these features are huge, right? So P is of the order of hundreds of thousands. I mean, even scanning through all the coordinates can be very expensive, or even taking a gradient can be expensive. Okay, so I mean, we need to devise ways to circumvent that. So basically, assuming that the solution has support size small, which is the problems that we are looking at, we use active set updates. And first order methods, this is one thing that is very good with first order methods. It is very good at exploiting warm starts across, it's very good at exploiting warm starts. So basically, it can exploit warm start information across the different nodes of the branch and bound tree. There is another method that is very useful that we found out, that is the notion of gradient screening. Again, it goes to the point that if you want to calculate the gradient, it can be very expensive. We don't want to calculate the gradient entirely. Okay, so here are some experiments. Okay, so the experiments are, again, the choice of the solution, the runtime depends upon the choice of lambda 2. If your lambda 2 is very large, the runtimes are going to be very fast. But the way in which we chose lambda 2 is such that it works well from a statistical viewpoint. Okay, because this is synthetic data set, we know what value of lambda 2 is going to work well. Okay, so this is the best choice from a statistical viewpoint. All right, now let's see how commercial solvers are working. So Guru B can solve up to P equals to 1000, and then it basically stops. Mosaic is better over here, probably because its relaxation solvers are very good. Okay, and this is an outer approximation method. All right, now this approach L0B and B can actually go up to solve all these problems. Okay, this synthetic data n equals to 1000 samples, but the number of features can go up to 10 to the power 6. Okay, if the value of lambda 2 is larger, then of course the runtime becomes smaller. But again, this is better from a statistical viewpoint compared to this. So there are many other experiments in the paper that we do on variable cap big M and so on and so forth. This is, I think, the largest data set that we tried, where P is of the order of 10 to the power 7. This is a real data set. And it gives you solution as long as the number of non-zeros is not too large. It kind of is okay in giving you solutions. Okay, of course, there are some cases where the runtime actually blows up. But again, we do not know actually why it happens, but this is something that we would like to understand actually why it happens. All right, so I think with that, I'll get to the conclusions. So again, so what I'd like to end with is by saying that there are a lot of estimators in statistics and machine learning, which are discrete, but they have a lot of structure in them. Okay, and I do think that their mathematical optimization methods, and especially techniques from both convex and integer programming, they actually provide a rich framework for the modeling and computation for these difficult-looking problems. Okay, so again, I shared with you some of my experience because of using techniques from convex optimization and integer programming to address these problems. But I do think there is a tremendous scope of developing new algorithms and better understanding what works for what classes of problems, what does not work for what classes of problems, and so on and so forth. And something that I did not get a time to talk about, but this I think is also exciting, that is, can we use statistical ideas to take an integer programming formulation? So I have an integer programming formulation, which may be difficult to solve with current integer programming technology. Okay, now, can we reformulate that problem using statistical modeling ideas into something else? And then this something else turns out to be easier to solve using current integer programming technology. Okay, so I think this is an area where I'm particularly excited about, that I'd like to understand even more. All right, thank you.
Thank you, Professor Mazumder, for a wonderful talk. We have time for questions, so. Yep, Lao Song.
Yeah. So Rahul, you give a very, very nice talk. I mean, I really enjoyed. So I have like one question is regarding the formulation. I think it's just a few, I think the slides at the very end.
Sure.
You have like second order cone relaxation, some kind of.
Yes, this one.
Yeah, so beta square, yeah, that one.
Mm-hmm.
So beta square is quadratic, right? So you still, the first part is also quadratic. Why you needed to do this second order cone for that last part?
Yeah. So if you do this is the part which actually gives the perspective formulation. Basically, they say that if you actually do this, if you look at the convex relaxation of this, it turns out to be a tighter you'll get a tighter relaxation of this. If you do this.
One. Okay.
Yes,
tighter relaxation.
Yeah, okay. You get a tighter relaxation with this instead of versus not doing this at all.
Okay. All right. So yeah, and for the local search, you basically you cannot guarantee you will find the global optimal solution, right?
No. And this is something that we try to examine. I think we can show that it is going to lead to global solutions on very specialized toy problems, but more generally, we cannot show it theoretically.
Okay. So do you have like something like, say, if you do local search, you cannot get that suppose you cannot escape from the neighborhood, and also the solution may not be great, then is there any way to check or something?
Yeah, it can happen. I definitely agree. It can happen. I'm not saying local search is going to make everything, is going to solve everything. So here is a place where it is not going to work, right? Suppose you have a lot of these minimas, right? And the minimas are very, very well separated. Mm-hmm. Okay. And you are at a solution, right? But probably the minimum, the actual global minimum is somewhere else. Okay, far apart. If you go and trying and improve, take local moves to decrease, it may be possible that it is never going to come over here. It may happen.
Sure.
But here is a thing. Okay, here is a thing. Here is a place where we see the local search is going to make a difference. Okay, so in this example, I was showing an example where local search really does well. So if you look at this, right, the correlation of effect over here, there is a pairwise correlation, is very high. Rho equals to 0.9. 0.9 is very high. Okay, you see that there is a difference. Now let's look at an example like this. Look, the correlation is much smaller. Okay, I look at exactly the same thing, the probability of full recovery. And then if I look at this, let's see what happens between L0 and L0 swaps. L0 is the coordinate descent and L0 swaps is over this, right? They're literally overlapping. Okay, so this is a case where just coordinate descent is good enough for this problem. It is basically giving you the global minimum. Okay, I mean, statistically it is giving you the global minimum because it's giving you optimal support recovery. But if you start doing if you do local search, probably you'll improve a little bit in terms of objective, but probably not. It's not helping. So I think this is a place where you will really see a benefit in terms of correlation.
Okay.
Okay, so again, so I would say this becomes this becomes a place where we really do not know. We see in some cases it actually works, but also a priori, right? If you give me a real data set, it's very difficult to say a priori whether a local search is going to lead to improvements or not, unless you try it out and then see. These are all synthetic data sets, and post hoc I can study the structure of the synthetic data sets and say probably this is the reason why. But in general, in reality, it's very hard to say.
Do
Unless
they
you have the
also
tools.
give you global optimal solution, like those branch bound approach, like that do not use the local search? Those, I mean, they will give global optimal.
Yeah,
solution.
absolutely, they will.
Yeah.
So this paper we wrote before, and so before the global branch and bound stuff. But I would still say that the approximate solutions are more practical compared to global branch and bound methods, right? And also the approximate solutions, we really need the approximate solutions to even start our branch and bound solver, right? When we start the branch and bound solver, we need a very, very good initial solution. If you have a bad solution, then the size is just going to explode of the branch and bound method. So we definitely need this. There is another place where local solutions are needed. So for example, in reality, when you do not know what the tuning parameters are, right? So this is a problem that you want to solve. You do not know what lambda q is or lambda 0 is. You do not know a priori what it is. You have to solve them on a sequence of lambda q and lambda 0 values, like the cross validation stage. Then what would you do? Would you solve an IP on each of these problems? I mean, that's way too much computational resources. Probably you need a very good heuristic solution to get a choice of lambda q and lambda 0 or a neighborhood. And then you use IP to certify optimality.
Yeah. Yeah.
So maybe we can stop the official part of the seminar here. Thank you once again.